Welcome back. This will be a video lecture on Section 2.2 of the textbook, Direct Methods for Solving Linear Systems. I'm going to cover this section in two different video lectures, and this will be Part A. Now, the section has been divided up into 6 parts: echelon form, elementary row operations, and Gaussian elimination. I'll cover that in Part A, and then we'll pick up Gauss-Jordan elimination, homogeneous systems, and linear systems in Z sub P in Part B of the lecture. So let's begin with the echelon form. Before we begin talking about the echelon form in earnest, let's make a disclaimer. Consider this system of equations here. Here's a system of 3 equations and 3 unknowns. Now, there are 2 natural matrices associated with this system. One is to embed the entire system in what's called the augmented matrix, and this carries all of the information about the system. It contains information about the coefficients and the column of constants. Another natural matrix associated with this system, and this will be especially important in later parts of this course, is simply the matrix of coefficients, where we lift the coefficients off of the system and place them into a matrix, in this case a 3x3 matrix. Both of these matrices are very important, and I just want to say that all of the content of this section can be applied to the augmented matrix, and it can be applied to the matrix of coefficients. In the last section, we learned how to create equivalent systems using row operations. The idea was something like this. We would take a system of equations, encode it in an augmented matrix, and then use row operations to form an equivalent system of equations that's easier to solve. So for example, this system on the right can be solved very easily by back substitution. Now we want to pay special attention to these entries that I've colored in red here. These are the first non-zero entries that we hit in each and every row of this augmented matrix, and these have a special name. So the first non-zero entry in each row is called a leading entry. So here's the technical definition of row echelon form. A matrix is in row echelon form if it satisfies the following properties. First, any rows consisting entirely of zeros are at the bottom. And second, in each non-zero row, the first non-zero entry, called the leading entry, is in a column to the left of any leading entries below it. Now, the easiest way to begin to understand this idea of row echelon form is to look at a couple of examples. All of the matrices in this list are in row echelon form. Let's take a look at a couple of them in detail. In this first example, this matrix contains a row of zeros, but that row of zeros is appearing at the bottom, so this conforms to rule number 1. Now let's take a look at rule number 2. The leading entry in row 1 is this 2, and the leading entry in row 2 is this -1. Now what do I want to see? As I work my way down through the rows, I want to see the leading ones marching to the right. And so this conforms to rule number 2. So this matrix is in row echelon form. Another interesting example here is the third matrix. Let's check. The matrix contains a row of zeros, so in that row of zeros is at the bottom, so this conforms to rule number 1. The leading entries are the 1 here in row 1 and the 1 here in row 2. And again, as I work my way down through the rows, I see the leading ones marching to the right. So one reason why this is an interesting example is so that we don't misinterpret rule number 2. Rule number 2 doesn't say that as I march down through the rows, the next leading entry has to be in the next column. It just has to be to the right. So as I move down, I just need to move to the right to find the next leading entry. It does not have to be in the next column. Which of the following matrices are in row echelon form? Let's begin on the left with this matrix. Now, this matrix doesn't contain a row of zeros, so there's nothing to check for rule number 1. So we have to check to see if the leading entries are behaving properly. So our leading entries are the 3, the 2, and the 4. Now as I march from row 1 down to row 2, I am marching to the right to my next leading entry. But as I move from row 2 to row 3, I have to move to the left to find the next leading entry. And this is violating rule number 2 of row echelon form. Now, there's an easy fix. If I simply swap row 2 and row 3, this will be in row echelon form. So we're one row operation away from getting this into the row echelon form. Let's take a look at this matrix here in the middle. Now, this matrix does contain a row of zeros, and it's not at the bottom of the matrix. But once again, I can do a simple row swap. If I swap row 2 and row 3 in this matrix, it will be in row echelon form. So once again, there's an easy fix for this matrix. Now let's take a look at this last example. There isn't a row of zeros, so there's nothing to check. I can see a leading entry of a 2 here in row 1 and a leading entry of a 1 in row 2. And as I march down from row 1 to row 2, I do march to the right to find the next leading entry. So this one is in fact in row echelon form. Now, if my matrix is in row echelon form, I'm very happy because the associated system of equations can easily be solved by back substitution. So, if I can take any system of equations and show that it's equivalent to a system in row echelon form, I will have achieved something because I can now easily work out the solution set for that system of equations. So we've been hinting at this already, but the mechanism by which we can turn any system of equations into a system of equations in row echelon form is through elementary row operations. There are 3 elementary row operations, and I already introduced you to these in section 2.1. So let's remember that there's a type 1 operation, which is simply switch any pair of rows. There's a type 2 operation, which is take any row and scale it by a non-zero number. And then there's the type 3 operation, and this is the most obscure operation. We can think of this as copy, scale, and add. I take any row, make a copy of it, scale it, and then add it to another row. Now, the important thing to know is that a matrix can be converted to row echelon form through a sequence of elementary row operations. All right, so a matrix can be converted to row echelon form simply by following a recipe consisting of elementary row operations. Now, we're going to want to keep track of our row operations as we convert our matrix to row echelon form. So we're going to need some notation to kind of help us keep track of our steps along the way. So let's take a look at some notation that we would use for a type 1, a type 2, and a type 3 operation. So here's an example of notation to notate a type 1 operation. So we're just going to use the double arrow to say that row 1 and row 3 are being exchanged. Okay? Here's a typical notation for a type 2 operation. Row 4 is being scaled by a factor of -2. All right? And here's typical notation for type 3. Now we have to be careful in a type 3 operation since there's 2 rows that are in play here, right? There's the row that's acting. I'm making a copy of a row, right? I'm scaling it. And then there's the row that's receiving the action, right? So in some sense, the object of the operation. And the way this textbook does it, it lists the row that's receiving, right, at first, and the row that's doing the acting is listed second. So in this notation, I'm taking row 1, I'm scaling it by -2, and then I'm adding it on to row 3. So you just have to get used to this. Every book is going to be slightly different in regard to how it notates a type 3 operation, but in this text, the row that's listed first is going to be the row that's changing. That's the row that's being affected. Okay, so this is the notation we will use to keep track of our elementary row operations as we convert a matrix into its row echelon form. Let's put all this to work. Let's use elementary row operations to put the matrix below into row echelon form. So join me at the document camera to work out the details of this problem. Welcome to the document camera. Our goal is to convert this matrix into a row echelon form. And I'm going to begin with this 1 here. I'm going to use this 1 to eliminate the 3 and the 1 that sit below it in rows 2 and 3 respectively. Now, let's think first about this 3. What I can do is I can multiply row 1 by -3 and add it on to row 2. Now, in the notation that we're adopting here, we're affecting row 2 by adding a multiple of row 1, in this case, -3 times row 1 to it. Now, let me show you a trick that's time saving. I'm also going to use row 1 to affect row 3. And so I'm going to use a multiple of -1 times row 1 onto row 3. And I'm going to do both of these not at the same time, but in the same step. So I'm also going to affect row 3 by adding -1 times row 1 to it. All right, and this is pretty typical to, if you're using row 1, for example, to make effects on row 2 and row 3, it's typical to combine those together in one step. All right, my new matrix. The only row that's not changing is row 1, so let me write that one. 1, 3, 1, -4, and 1. Now there are going to be changes in row 2 and row 3, so let's take a look at the change in row 2. Remember, I'm multiplying by -3 and adding down. So this will be -3 times 1 added down, that's going to be 0. -3 times 3 is -9 added down onto the 9 is going to be 0. -3 times 1 is -3 added onto the 5 is 2. -3 times -4 is -12 added onto the 2 is 14. -3 times 1 is -3 added onto the 19 is 16. And so that's the new row 2. Now let's check out what happens in row 3. Remember, I'm multiplying by -1 and adding down, so I'm going to get a 0. -3 onto 3 is 0. -1 onto the 2 is going to give me a 1. When I multiply by -1, that gives me a 4. Added onto the 2, I get a 6. And then -1 onto the 1 is -1. I add that onto the 7, and I get a 6. Okay, now the next thing I'm going to do is I'm going to scan down row 2, and I encounter the first non-zero entry here. So I'm going to think of this as a leading entry, and I'm going to use it to eliminate the one that sits below it. Now the first thing I'm going to do, and this is just, you don't have to do this, but this is just to make my life easier. I'm going to try to turn this into a 1 because that makes this next elimination step easier. So I'm going to scale row 2 by a factor of 1/2. Now in this case, row 1 is unchanged. And row 3 is unchanged. And row 2 is going to change because I'm scaling it by a factor of 1/2, so the new entries are going to be 0, 0, 1, 7, and 8. Okay, my next and last step is going to be to use this 1. I'm going to think of that as my leading entry, and I'm going to try to eliminate this 1 that sits below it. And so I can do that with a type 3 operation. I want to have an effect on row 3, so I'll list that first. And how am I going to affect it? I'm going to take -1 times row 2 and add it on to row 3. So in this case, 1 and 2 are unchanged. But 3 is changed according to this recipe. So I'm multiplying by -1 and adding down. So I'll still have 0 here. I'll still have 0 here. -1 times 0 added on to 0 is still going to be 0. I'll see a change here. I'm multiplying by -1 and adding down, so this will now become a 0. I'm multiplying by -1, so this will become a -7. I'm adding it on to the existing 6, so that will become -1. And then finally, I'm multiplying the 8 by -1 and adding it onto the 6, so that will become a -2. And now I claim we're in row echelon form, so we're done. Let's just double check. There are no rows of 0, so there's nothing to do there. And when I look at my leading entries, in this case, this will be the 1, and the -1. As I move down through the rows, the leading entries are snapping to the right. And so this is going to be row echelon form, and we can stop. All right, so let's go back to the class notes and continue. This next observation has many important consequences. Each of the elementary row operations is reversible. Now let me give you an example, a concrete example in each type. So for type 1, imagine I take a matrix and I switch row 1 and row 3. I can easily reverse that by taking that matrix and switching row 1 and row 3 once again. So switching row 1 and row 3 and then doing it again will bring me back to exactly where I started. All right, imagine I take a matrix and I scale row 2 by a factor of 1/3. Well, I can restore that matrix to its original order by simply taking row 2 and scaling it now by a factor of 3. So I can invert this operation by applying this operation, okay? Now, this one's a little more difficult, but we can handle this. This is a type 3 operation. In this notation, I'm making a copy of row 2, I'm doubling it or multiplying, scaling it by a factor of 2, and adding it to row 4. If I want to undo that, I can simply take a copy of row 2, now multiply by -2, and add that onto row 4. And that will undo the effect of this first elementary row operation. So each and every elementary row operation can be inverted or reversed by another elementary row operation of exactly the same type. Now let's work a problem to reinforce this concept. So a matrix A is reduced to the matrix B through the following sequence of row operations. So we have a sequence of row operations that were applied to a matrix A that have brought it to this matrix B. And so here's the list of the row operations. We can see we've got a type 1, a type 2, and then a sequence of type 3 operations that have reduced A to B. Now the question is, given that we know what B looks like, what is the matrix A? So join me at the document camera. Let's work through this problem in some detail. All right, welcome to the document camera. In this problem, there's an unknown matrix A that's been reduced to this matrix B through this sequence of row operations. Now what we want to do is we want to try to figure out what this matrix A is. And the idea is this: if this is the sequence of operations that brought us from A to B, then by undoing each of these operations in reverse order should bring us from B back into A. So we're basically going to take these operations, reverse the order in which they were applied, and reverse each of these operations. So we're going to have 5 operations to take us from B to A, and it's going to look something like this. So let's list them. 1, 2, 3. Our first operation has to undo operation 5 here, and that's a type 3 operation with a -1 scaling. So we're going to simply use another type 3 operation. It'll be row 3 plus 1 times row 2. We simply have to change the sign. Again, we can undo this type 3 operation. This will be row 1 plus 2 times row 2. This third one, again, is a type 3 operation, so we can undo it with another type 3. So this will be row 2 plus -1 times row 1. All right? We can undo this scaling by simply using a multiple of 2 instead of the 1/2. So we'll do 2 times row 1. And we can undo this row switch by just repeating the row switch. So we'll do row 1 and row 2 switch. Okay, now we're not going to have enough room to finish the problem on this piece of paper, so I've written this matrix on another piece of paper, and I'll just keep these row operations off to the side, and we'll apply them one after the other until we go from the matrix B to the matrix A. So our first step is going to be to apply this type 3 operation. So we're simply taking row 2, scaling it by 1, and adding it onto row 3. So row 1 is not changing. Row 2 is not changing. and I'm simply adding row 2 onto row 3. So I'm going to get a 0, a 3, and a 4. So that takes care of our first reversal. Now, we have to do another type 3 operation. This one is row 1 plus 2 times row 2. Now remember, in our notation, we're using row 2 to affect row 1. So row 3 is not changing, and row 2 is not changing. But now I'm taking 2 times this second row and adding it onto the first row. So I have to do 2 times 0, which is still 0, added onto the 1, which is 1. 2 times 3 is 6, added onto the 0, that's 6. And 2 times 2 is 4, added onto the 4, that's an 8. Okay, let's continue here. We have to do another type 3 operation. This one is going to be row 2 plus minus 1 times row 1. Okay, so row 2 is the one that's being changed. So row 1 is unchanged, 1, 6, 8. And row 3 is unchanged, 0, 3, 4. Now row 2 is being affected by row 1. I'm multiplying by negative 1 and then adding down onto row 2. So negative 1 times 1 is negative 1. Added onto the 0 gives me a negative 1 here. I get a negative 6. And I add that on to the 3. That's going to give me a negative 3. Then I'll have a negative 8. Added onto the 2 is going to give me a negative 6. Okay, now that takes care of our first 3 reversals, and those were all type 3. The next thing we have to do to undo the scaling is to do another scaling. We have to do 2 times row 1. Okay, so I'm going to take row 1 and simply scale it by a factor of 2, so that'll bring me to 2, 12, and 16. All other rows unchanged. And then my final move to undo it and to restore our matrix A is to do a row swap. I'm going to switch rows 1 and 2. And that's very easy. We just take that existing row 2 and the existing row 1 and we switch their places. And then we rewrite row 3. And the claim is that this must be the matrix A that we started with. That matrix A, if I take that matrix A that I've written here and I apply this sequence of steps, it should bring us to the matrix B. If I reverse those steps, I can take B back to A. So this is really just an exercise to show us what? That the elementary row operations are reversible, and that I can take a matrix I can take this matrix B, and by reversing all the steps and reversing the order, I can restore the matrix. I can restore the matrix A that I started at, okay? All right, so let's head back to the class notes. Now this following terminology is very helpful. Matrices A and B are row equivalent if there is a sequence of elementary row operations that converts A into B. Let's look at this theorem together. Matrices A and B are row equivalent if and only if they can be reduced to the same row echelon form. Let's go to the document camera and examine the proof of Theorem 2.1. All right, welcome back to the document camera. We're going to prove Theorem 2.1. And let's just remember that since it's an if and only if statement, I have to prove 2 things. That if A and B are row equivalent, then they can be reduced to the same row echelon form. And if they have the same row echelon form, they are row equivalent. So let's take a look at the forward direction. Let's start by assuming that A and B are row equivalent. Now what does that mean? That means that I can carry the matrix A to the matrix B by some sequence of elementary row operations. So let's just denote that by this shorthand. I can take A to B by some recipe, some list of elementary row operations. So let's call that, we'll just denote that by elementary row operations. Okay? Now we know that B can be carried to some row echelon form by, again, another sequence of elementary row operations. So let's denote that this way. We'll say B can be carried to some matrix R, and this is going to be in row echelon form, through a sequence of elementary row operations. Now, to keep these distinct from each other, I'll put a subscript 1 on this one. So there's a first recipe that takes A to B. And then there's a second recipe, another sequence of elementary row operations. I'll put a subscript 2 on these that carries B into this row echelon form matrix R. Now, I want to show that I can also carry A to R. And all I have to do is follow recipe 1 by recipe 2. So if I take the matrix A, I'm going to need a very long arrow for this. And I first apply recipe 1, and then follow it by recipe 2. In the middle, at some point I'll be at B, but then I'll keep going, and I'll end up at R. So if B can be taken to this matrix R and R is in row echelon form, then A can be taken to that same row echelon form. So we've shown that if A and B are row equivalent, then we can reduce them to the same row echelon form. In this case, we're calling it R. Now we have to show the other direction. Okay, we have to show that we have to assume that they can be reduced to the same row echelon form. So let's say A and B can be reduced to the same row echelon form. Now, what are we saying? We're saying that there's a recipe that takes A to some row echelon form, let's call it R, and another recipe that takes B to that same row echelon form R. So let's say A takes, we can take A to R, and we'll say that this is some recipe of elementary row operations, subscript 1. And I can take B to the same, right? This is what this is saying. I can take it to the same row echelon form by a sequence of elementary row operations, a possibly different set of row operations. So I'll call this one subscript 2. So I can take A to R through this recipe, and I can take B to R through this recipe. Now I have to find some way of chaining A to B through some sequence, through some recipes. So here's what I'm going to do. I'm going to take A to R using recipe 1, and then I'll invert this relationship. I'll take this sequence of elementary row operations, I'll reverse all of them, and I'll also take them in reverse order, just like we did in our exercise, our previous exercise. So I'll notate it this way. I'm going to start at A. I'm going to apply recipe 1. That's going to take me to R. And then starting at R, I'll invert recipe 2. I'll write it this way. I'll say it's the inverse of recipe 2, and that means two things, right? It says I'm inverting every step, and I'm taking the steps in the reverse order, just like we did in our previous problem. So what's going to happen? I'm going to follow these steps. I'm going to go from A to R, and then once I'm at R, I'll reverse all of these steps, and I'll go from R to B. And now I've got one colossal recipe of elementary row operations that carries me from A to B. And that's precisely what it means to say that the matrices A and B are row equivalent. So this gives us the proof of theorem 2.1. Let's not forget our goal. Our goal is to solve systems of equations. And so let me suggest to you a method. This is called Gaussian elimination. Gaussian elimination has 3 steps. In the first step, we want to write the augmented matrix of the system of linear equations. So we're going to convert our system of equations into an augmented matrix. In step 2, we're going to use elementary row operations to reduce the augmented matrix to row echelon form. And then finally, in step 3, we're going to use back substitution to solve the equivalent system that corresponds to the row-reduced matrix. Now let's work a problem using Gaussian elimination. A system of equations in the variables x, y, and z has this augmented matrix. Place the matrix into reduced echelon form and describe the solution set of the system. So let's head over to the document camera and look at the solution to this problem. All right, welcome back to the document camera. Let's take a look at this problem in some detail. So, some system of equation has generated this augmented matrix, and now we want to explore the solution set to this system by putting it into a reduced echelon form through a sequence of row operations. Now, what I'm going to do is use this leading entry, this 1, to eliminate, in this case, the -1 in row 2 and the 1 in row 3. Now I can do this kind of at the same time. Let me show you. So I'm going to multiply row 1 by 1 and add that onto row 2. And that's going to have the effect of turning that into a 0. And I can multiply row 1 by -1 and add it onto row 3. And that's going to have the effect of turning that into a 0 as well. So I can do both of these at the same time since I'm using row 1 to consistently change, in this case, rows 2 and 3. Now, row 1 is not going to change. It's going to stay as 1, 2, -5, and -3. Let's check out the change in row 2. When I multiply by 1 and add down, it's simply going to be the 1 added to the -1. That's a 0. The 2 will be added to the -2. That's also 0. The -5 added onto the 7 will give me 2. And the -3 added onto the -9 is -12. Okay, that changes that. Now let's look at the effect in row 3. I'm simply multiplying by -1 now and adding down. So that'll be -1 onto 1 is 0. -2 onto 2 is also 0. Now I have to be careful here. That's 5 added onto 1. That's going to be 6. And 5, excuse me, I did that one. 3 added onto 18 is going to be 21. Okay, now I'm going to go down row 2. I'm going to hit this leading entry, this 2. I'm going to use that 2 to eliminate the 6 that sits below it. And so I'm in luck because 6 is a simple multiple of 2. It's just 3 times 2. So I can affect this change. I can take -3 times row 2 and add that on to row 3. All right? And so what is this going to look like? Let's take a look. I know that row 1 is not changing. Row 2 is not changing. Now row 3 is being changed according to this recipe. So remember, I'm multiplying by -3 and adding down. So that'll still be 0 plus 0 is 0. -3 times 0 is 0. Added on to 0, that's still 0. -3 times 2 is -6. Added on to the 6, that's 0. And now I've got -3 times the -12. That's going to be a positive 36. When I add that onto the 21, that's going to give me 57. And so this is now considered in row echelon form. This matrix is in row echelon form. I can see my leading entries are going to be this 1 and this 2 in the coefficient matrix, and then I'll have this 57 sitting over here in that column of constants. Now, how do we interpret this? Now, we've got it in row echelon form. How do we interpret this? Now, I would say the jarring thing is right here. And this is And this is what I'm about to say is going to apply anytime you see this. We have a row of zeros in our coefficient matrix paired up with something non-zero in the constants column. And if we reinterpret this, let's say our variables are x, y, and z. If we interpret this, this is saying 0x plus 0y plus 0z is equal to 57. And that's a contradiction. Okay? That's a contradiction. And that is a sign that our system has no solutions. It's an inconsistent system. Now, if you remember our theory that we've been developing, right? This sequence of operations that we've conducted always maintains equivalence, right? So the solution set to this system is inconsistent. We reach a contradiction, 0 equals 57. So there are no solutions to this system, and by equivalence, there are no solutions to this system. This system is also equivalent. So when we reach such a contradiction like this in our reduced echelon form, when we reach a contradiction like a row of zeros in our coefficient matrix is matched up with a non-zero entry in our constants column, we can declare the system inconsistent and say that the original system has no solutions. Okay, that's an interesting example. I've got another one cooked up for you. Let's go back to the class notes and take a look at that. A system of equations in the variables x, y, z has augmented matrix given below here. Place the matrix into row echelon form and describe the solution set of the system. Let's go to the document camera and take a look at this problem in some detail. All right, welcome to the document camera. Our first step is going to be to take this matrix and use Gaussian elimination. We're going to first put it into a row echelon form, and then we'll use this process of back substitution to solve the system. So here's what I'm going to do. I'm going to use this leading entry, this 1 here. I'm going to eliminate the things that are in its column. So I'm going to eliminate that -2 in row 2, and I'm going to eliminate the 3 in row 3. And this can be done with some type 3 operations. So let's do both of them in the same step here, so to speak. Okay, so I'm using row 1 to have an effect on rows 2s and 3. So row 1 is not going to change. Now I want to eliminate this -2, so I'm going to scale row 1 by 2 and add that on to row 2. I also want to eliminate this 3 here, so I'm going to scale row 1 by -3, and I'm going to add that onto row 3. Okay, so let's see what the overall effect is going to be. So I'm multiplying by 2 here. I'm going to change row 2 first. I'm multiplying by 2 and then adding down. So 2 onto the -2 is 0. 2 onto 1 is 2. Add that onto the -1. That gives me a 1. 2 onto the -6 gives me a -12. Add that on to the 10. That's a -2. And then 2 times the 1 is the 2. Add that on to the -8. That's a -6. Okay, let's change row 3 now according to this recipe. So I'm multiplying by -3 and adding down. So that's going to be a 0. This will become -3 added onto the 5. That's 2. When I multiply by -3, that becomes 18. And when I add 18 onto -22, I'll have -4. And then finally, when I multiply by -3, that's -1, added on to the existing -9, that's -12. All right, so far so good. Now I'm going to go down row 2 until I hit something non-zero. Here's a 1. I'm going to use that 1 to eliminate this 2 below it, and that should get me to row echelon form. So my next step is going to be a type 3 operation. I'm going to scale row 2 by -2, and I'm going to add that on to row 3. Okay, so remember, row 3 is the only row that's changing here, so I'm going to rewrite row 1. I'll rewrite row 2. And then finally, I'll change row 3 according to this recipe. So I'm multiplying by -2 and adding down, so that stays as a 0. That becomes -2. Onto the 2 gives me a 0. When I multiply by -2, that's 4. Added onto the -4, that's a 0. And then multiply the -6 by -2, that's a 12. Added on to the existing -12, and that's a 0. Okay, now at this point, we're in row echelon form, and all of our elementary row operations are done. We can just rest with that. Now we have to go through the process of interpreting this row echelon form and getting a solution set out of this. Now, let's remember our variable names are x, y, and z, and it's best to work from the bottom up. So let's first interpret this equation. There's no content here in this row. This just says 0 is equal to 0. So the first equation of any content is right here. We know that y minus 2z equals -6. Okay, now I'm going to write that as y equals 2z minus 6. So one thing I can get out of that second equation here is that there's a relationship between y and z that I can express as y equals 2z minus 6. Now if I look at this first equation, I get a relationship in x, y, and z, right? It's going to be x plus y minus 6z is equal to 1. But I know from above, all right, I can replace the y by 2z minus 6. So in principle, I can write x in terms of z. So let's do that. Okay, so I simply replace y by 2z minus 6. And now let me just clean this up a little bit. So that's going to be x minus 4z minus 6 equals 1. So when I solve for x, I can write x as 4z plus 7. Okay, so here's what I have at the end of the day. I know I can write x as 7 plus 4z. I know I can write y as a -6 plus 2z. But my equations don't bind z in any way, right? I've got 3 variables, but I only have 2 equations, and so there's no way to bind z to any specific value. I know that as I set different values for z, I can set a value for x and a value for y correspondingly, but there's nothing that binds z to be anything in particular. So typically what we do in a situation like this is we just imagine that z is now free. It's free to kind of take on any value it wants. But once we set the value for z, that sets up a value for y, and it sets up a value for x. So typically what people do here is we'll say z is going to be equal to some parameter. We'll call it s. So think of s as a parameter. We can run it through all the different real numbers. Now once I set z equal to s, that sets a y equal to a -6 plus 2s. And it sets x equal to 7 plus 4z, which in this case will be 4s. Okay, now this actually looks better if I think of it in vector form. Because I can write this as a sum of 2 vectors. So what I'm doing is I'm separating out the parts that are just constants. So 7, -6, and an implied 0 here. And then a 4s, a 2s, and an s. And then I'm going to scale the s out. I'm going to take the s out here. And I'll write the final answer as in writing our solution this way, we can see that the solution to the original problem, right, the set of all solutions to this original problem, is infinite in extent. There's an infinite number of solutions, but they actually have a nice geometric interpretation, right? This is the equation of a line, right, the vector form of a line through this point 7, -6, 0 with direction 4, 2, 1. So we know that there's not a unique solution to this. This is a set of 3 different planes in three-dimensional space. And so rather than intersect at a unique point, it turns out that they intersect along a line. And we can actually describe that line, right? It's got a point on it with coordinates 7, -6, and 0. And the line is pointing in the direction given by the vector 4, 2, 1. Okay, let's go back to the class notes and continue our discussion of systems of equations. Now I want us to reflect upon the example we just worked, and I want us to pull a couple of important concepts out of that example. The first concept is the distinction between what are called leading variables and free variables. So if a variable contains a leading entry in its column, then we will call it a leading variable or a bound variable. And if a variable is not a leading variable, then we will call it a free variable. So consider the system in the variables x, y, and z given below. The leading variables are x and y, and the free variables are z. Let's make sure we understand why. So if the columns are labeled x, y, and z, we can see that column 1 contains a leading entry, and so its variable x will be a leading variable. Column 2 also contains a leading entry, and so its variable, y, will also be a leading or a bound variable. The third column, the column that corresponds to the variable z, does not contain a leading entry, and so it will be considered a free variable. So x and y are bound, and z is free. Our second important concept is the concept of rank. The rank of a matrix is the number of non-zero rows in its row echelon form. So in our example, we started with this augmented matrix on the left, and through a sequence of elementary row operations, we put it into this row echelon form. Now there is a row of zeros, but there are 2 non-zero rows in the row echelon form, so the rank of this matrix is 2. Now that is equal to the number of leading entries in the row echelon form. We are now ready to state and prove the rank theorem. Let A be the coefficient matrix of a system of linear equations with n variables. If the system is consistent, and that means if the system has any solutions at all, then the number of free variables should be equal to n, the number of variables, minus the rank of A. Let's go to the document camera and explore the meaning of this theorem and its proof. All right, welcome to the document camera. Let's just talk a little bit about the rank theorem, and let's try to remove some of the mystery in the statement of the rank theorem, because once you boil it down, I think it's saying something relatively straightforward. We just have to kind of understand how all of the notation and concepts that we've developed are coming to the fore in the statement of this rank theorem. So I think rather than look at this in general, let's look at a specific example. Let's imagine that we started with a system of equations, we embedded it in an augmented matrix, we went through a long sequence of elementary row operations, and let's say we got down to this final form. This is our reduced echelon form. Now, we're told that the system is consistent, and so that says that any rows of zeros on this side, the coefficient side, would have to be matched by zeros on that other side. So the system is consistent. There's nothing inconsistent in anything about this system. So let's just concentrate on what's happening above the rows of zeros, because this is where all the content is. Now, what we've got in this case 4 variables, which I've just labeled x, y, z, and w. And what we want to do is we want to separate these variables into the 2 types. Now, we've got leading entries here in row 1 and here in row 2. And the variables that are associated with them through their columns, those are called leading variables, right? So, or bound variables, however you want to think about it. So let's label this one L for leading, and we'll label this one L for leading. The variables y and w, since they are not leading, since they don't inhabit columns that contain leading entries, those are labeled free. Okay, and so we've got our four variables separated into two types, right? The type that are leading and the type that are free. But we'll notice that that exhausts all of the variables. Every variable has to either be of the type L or of the type F. Now, in our example, we can see that the number of leading plus the number of free is adding up to 4, the total number of variables. And that's always going to be true, no matter how big our system is. So let's kind of generalize this part of it, right? We're saying that the number of leading variables, the number of L, plus the number of F-type variables, always has to equal the number of variables n. And that's what we're being told in this problem, is that there are n variables. So that's just saying the number of leading variables plus the number of free variables has to add up to the total number of variables. In our situation, the 2 plus the 2 has to give us the 4. Okay, now let's solve this for the number of free variables, because that's what how the rank theorem is posed, right? This says that the number of free variables, right, has to be the total number of variables minus the number that are declared leading, that are associated with leading entries. Now, all we have to do is realize that every leading entry corresponds to a non-zero row. So the number of L is, by definition, just the rank of this coefficient matrix, right? That's just the rank of that coefficient matrix. And so by making this substitution, we can say that the number of free variables is simply n minus the rank of A. All right, so hopefully that'll take some of the mystery out of this. It's really as simple at this level. It's really as simple as saying every variable has to be of type L or type F. And that's where this begins, right? It just begins in that simple statement. The rest of it, the only other thing that we have to add to this is that when we look at our final rows, we have rows of zeros, but every other row has a leading entry in it, and therefore the number of variables of the type L has to equal the rank of this coefficient matrix. Okay, so there's a couple of very simple ideas that are put together. They form this rather mysterious looking statement, but when you boil it down, it's really as simple as that, okay? All right, so let's head back to the class notes and continue. I want to close this subsection on Gaussian elimination by working a couple of geometric problems with you. So in our first problem, if it exists, find the point of intersection of the lines given below in their vector form. All right, welcome back to the document camera. Let's take a look at this problem. Now, we've got an equation of a line in three-dimensional space, and we have the equation of another line in three-dimensional space. Both equations are being described in vector form, and the question is, do these lines meet in space, right? Because two lines in three-dimensional space don't necessarily meet. But if they do meet, what are the coordinates of their point of intersection? And we can answer this kind of question using systems of equations, Gaussian elimination, and reduced echelon form. Let's take a look at how we can think about this. If these lines did meet, that would mean that there's a value of t and there's a value of s that would make these vectors equal to each other. So let's write them out as, let's combine these pieces. This is going to be 5 plus 2t, 5 plus t, and 3 plus t. And this one could be written as 5 plus s, 7 plus s, and 17 plus 4s. Okay, so that's a way of writing them as single vectors. So if these lines did meet in space, there would have to be a value of t and a value of s that would make these two vectors equal to each other. So the condition for meeting, the condition for intersecting, is that 5 plus 2t, this first component, would have to equal that first component. that second component would have to equal that second component. And the third component would have to equal the third component. Okay, now we can rewrite these equations. Let's get all the variables on one side, and let's get all of the constants on the other side. So I'm going to keep the variables on the left, and I'll keep the constants on the right. And so I'll move this s over, and I'll write this as 2t minus s is equal to 0. The 5's canceling. All right, my second equation is going to be t minus s is equal to 2. And my third equation is going to be simply t minus 4s is equal to 14. Now, as an augmented matrix, I can just think of these as columns, and I can write this as an augmented matrix as 2, -1, 0, 1, -1, 2, and 1, -4, 14. And now the next step is just to go through the process of elimination here. Let's apply some row operations and clean this up, get this into reduced echelon form, and interpret the augmented matrix, that final augmented matrix. Okay, now I'm going to make my life a little easy here. I'm going to, it's easier to work with a 1 in this position, so I'm going to make a row switch here. I'm going to switch equation 2 with equation 1. You'll see why in just a second. So let's make that the new equation 1. This will become the new equation 2. Now, you don't have to do that, but it does make our lives a little easier. Because now this is my leading entry, and I want to use it to change that 2 into a 0 and that 1 into a 0. So I can do this by doing -2 times row 1 and adding that on to row 2. And I'll do a -1 times row 1 and add that on to row 3. Okay? Now when I do that, row 1 is not changing. Okay? Now row 2 is going to change according to this recipe. I'm multiplying by -2 and adding down, so that will become a 0. Okay? I'm multiplying by -2, so that's going to become a 2, and I'm going to add that to the -1, that simply becomes a 1. I'm going to multiply this by -2, so that's a -4, and when I add that onto 0, that becomes -4. Right, so I've done that elementary row operation. Now I'm going to have an effect in row 3 according to this recipe. Now I'm multiplying by -1 and adding down, so that becomes a 0. I multiply by -1, so this becomes a 1. I add down, that becomes -3. I multiply by -1, so that's -2. I add that onto the 14, that becomes 12. Okay, I'm almost there. I'm going to use this leading one now to eliminate the -3 below it. So I'm going to take 3 times row 2, and I'll add that on to row 3. Okay? So let's see what's not changing. Row 1 is not changing. Row 2 isn't changing. But row 3 is changing according to this recipe. So I'm multiplying by 3 and adding down. So that's going to become 0. That'll become 3 added on to the -3. That becomes 0. I multiply by 3. That becomes -12. I add that onto the 12. That becomes 0. Okay, we are now in reduced echelon form. Now we've got this row of zeros down here at the bottom, but there's no contradiction there. All right, that's not an inconsistency. That's a 0 equals 0 case. So all of our work is interpreting these first two equations. Now, remember that our variables were put in TS. So I've got T and S here. This second equation, right, in row 2 is telling me that S is equal to negative 4. Okay. And this first equation is telling me that T minus S is equal to 2. And so that says that T minus a negative 4 is equal to 2. So T plus 4 is equal to 2. Or T is equal to negative 2. Okay? So in fact, these lines do meet. The lines meet when S is equal to negative 4 and T is equal to negative 2. So by taking, and it doesn't matter, by taking either T equals negative 2 or by taking S equals negative 4, you can plug them into either one of these vectors and you'll generate exactly the same point of intersection. So let's get that point of intersection. I'm going to just work with T equals negative 2 with this vector here. So when I plug in negative 2, I'll have 5 plus 2 times negative 2, so 5 minus 4, so that'll be 1. 5 plus negative 2 is going to be 3. And 3 plus negative 2 is going to be 1. So there's our point of intersection. Now, just to show you, we could have just as well worked with this equation and S equals negative 4. Let's see how it would look if we'd used this vector instead with S equals negative 4. 5 plus a negative 4 is 1. 7 plus a negative 4 is 3. And 17 plus 4 times negative 4, so 17 minus 16 is 1. So whether we look at it by plugging 2 into this vector or by plugging negative 4 into this vector, they're going to get the same point, the point of intersection. That was the whole point of going through this process. All right, so in fact, these two lines do meet in three-dimensional space, and we know the coordinates of their point of intersection. All right, so I hope that that was an informative use of Gaussian elimination and an analysis of the reduced echelon form to solve a geometric problem. All right, let's head back to the class notes. Let U be the vector with components 1, 1, and 1, and let V be the vector with components 1, 2, and negative 1. In each case, determine whether the vector W can be expressed as a linear combination of U and V. In our first example, the vector W has components 2, 3, and 1. And in the second case, the vector W has components 2, 3, and 0. So join me at the document camera and let's see if any of these vectors W can be expressed as a linear combination of U and V. All right, welcome back to the document camera. Let's take a look at this problem. The question is, in part 1, can I combine these two vectors to form this vector? So if we think about what that's saying, can I find scalars A and B so that A times this vector plus B times this vector equals this third vector, 2, 3, 1. Now, you can see by comparing first, second, and third components that that's equivalent to saying, can I find A and B so that A plus B is equal to 2, A plus 2B equals 3, and A minus B equals 1. Now, the happy fact about this, if I rip this back and write this system as an augmented matrix, you'll see that it bears a strong resemblance to where we started. So we started here, we wrote down the corresponding system, and now I'm going to put this back in an augmented matrix, and let's see what we get. We're going to get 1, 1, 2. 1, 2, 3. And 1, negative 1, 1. So this is a nice fact. Anytime I'm doing a spanning problem like this, I'm trying to see, can I get to this vector from these two? It turns out the augmented matrix you get is you just take the column vectors and feed them in as the columns on the coefficient side, and you take the vector that you want to get to, so to speak, your destination vector, and that becomes this column of constants. So it's a nice fact about this spanning problem. I can just kind of feed these things into the augmented matrix immediately. And now, what am I going to do? I'm going to try to analyze this solution set to this system by performing some row operations. I'm going to try to work this down into reduced echelon form. Okay, now I'm going to use the 1 here. This is going to be my starting point. I'm going to use it to eliminate the ones that sit below it. Okay? All right. So I'm going to take a -1 times row 1, and I'm going to add that onto row 2. And I'll do another one of these. I'm going to take -1 times row 1 and add that onto row 3. So my recipe is going to be the same in both cases. I'm simply going to use this 1 to drop down and eliminate these ones that sit in its column. Okay, let's see what the effect is going to be. I'm going to still have 1, 1, 2 here. Okay, but now when I multiply by -1 and add down, I'll get a 0. I'll get a 1, I'll get a 1, and I'll do the same here now. Multiply by -1 and add down, so I'll get a 0. All right, I'm going to get a -2. And when I multiply, I'm going to get a -2 added onto the 1. That's a -1. Okay, so I get here. And now what I'm going to do is I'm going to go down my row 2 until I hit something different from 0. So here's my 1. I'm going to use that 1 to eliminate this -2 that sits in row 3. Okay, so what do I have to do? I have to take 2 times row 2 and add that onto row 3. Okay, let's see what we get. Row 1's not changing. Row 2 is not changing. Now row 3 is changing according to this recipe. So when I multiply by 2 and add down, that still stays as 0. I said row 2 wasn't changing, but then I changed it, so this should be a 1 here. Okay. When I multiply by 2 and add down, I get a 0. And when I multiply by 2 and add down, I get a 1. Okay, and now you can see the trouble here, right? This system is inconsistent. This last row is saying that 0a, 0 times a plus 0 times b is equal to 1, and that's a contradiction. In other words, the system is inconsistent. All right, so that means that this destination vector, right? This destination vector can't be reached by just using the vector 1, 1, 1 and the vector 1, 2, -1. There's more to this vector than just a simple combination of those two. So we can see the inconsistency here in the reduced echelon form, and that goes back to the original geometric problem and says you can't get there from here. Okay, now let's work the problem, or we change the destination vector. What if we choose 2, 3, 0 instead? So now I'm going to try to combine these two vectors to give me this third vector. Now we can, we can compare components and realize that this is a system in A and B here, or we can just realize that we can feed these things down into the columns of the augmented matrix. And there we go. Now we're off and running. We're going to do Gaussian elimination, and we're going to try to put this into reduced echelon form and analyze the resulting solution set. Okay, so it's not surprising that our steps are going to be imitating the steps we took above, because we're still working on this side of the matrix, and so we're still going to do the same kinds of steps that we were doing, right? So our first steps are still going to be scale row 1 by -1 and add it onto row 2. We're going to scale row 1 by -1 and add it onto row 3. Now, what makes this problem different is that this column is different, and so perhaps we'll get a different result here at the end. Let's wait and see. Now we're using row 1 to have effects on rows 2 and 3, so we're going to keep row 1 fixed. I'm multiplying by -1 and adding down, so that becomes a 0. That becomes a 1. That becomes a 1. I'm multiplying by -1 and adding down onto row 3, so that becomes a 0. All right, when I multiply by -1 and add down, that becomes a -2. And let's see what we get here now. When I multiply by -1, that's a -2. When I add down, that becomes -2. Okay, now we do see a difference, right? We see a difference over here. Let's keep going. I now look in my second row and I see this leading entry. So I want to make sure that the entry below it is a 0. So I have to change that into a 0. And let's affect that change with a type 3 operation. I'm going to hit row 2 by 2 and add that on to row 3. Okay. Row 1 is fixed. Row 2 is fixed. And now row 3 is changing according to this recipe. So when I multiply by -2 and add down, that's still going to stay 0. I multiply by -2 and add, I'm multiplying by 2. When I multiply by 2 and add down, I get a 0. When I multiply by 2 and add down, I get a 0. And now you can see that the difference, there's a fundamental difference here, right? This last row is a row of zeros. It's a set of zeros on the side of coefficients, and it's a set as a 0 on the side of the constants. That is not an inconsistency. That equation is just saying 0 is equal to 0. All of the content is up here. Now remember, our columns are labeled A and B. And so this equation here is saying that B is equal to 1. Okay? And this equation is saying A plus B is equal to 2. But if B is equal to 1, that says A plus 1 is equal to 2, or A is equal to 1. And so what this is telling us is that there is a recipe. It says if I set A equal to 1 and B equal to 1, then I can combine these two vectors to give this one. It says I should take 1 of this vector and 1 of this vector and combine them to get this third vector. Now that should be easy to check. If I take A equal to 1 and B equal to 1, I'm going to add 1 plus 1 to get 2, 1 plus 2 to get 3, and 1 minus 1 to get 0, so we can see that it works. All right, so we can see that subtle changes, these problems look very similar to each other, but in this case, this vector is not reachable, and in this case, this vector is reachable, and all we've done is we've just made a minor change in that third component, but that changes everything. We go from inconsistency to a nice, unique solution, and we can check to see that it works. All right, so this was a nice application of our work to these geometric problems. I hope you enjoyed that, and that closes off our section.